Okay, so we're going to spend the next few classes looking at solving logarithmic and exponential equations. So we'll look at solving these and verifying the solution, explaining why a value obtained may be extraneous. We'll solve exponential equations in which the bases are not powers of one another. We're going to look at problems involving exponential growth and decay. Also applications relating to loans, mortgages, and investments, and solving problems by modeling a situation with an exponential or logarithmic equation. A logarithmic expression is defined for only positive values of the argument. When we solve a logarithmic equation, it's essential to verify that the solution or solutions do not result in the log of a negative number. Any of those that do are called extraneous and are not valid solutions. So we're asked to solve, give answers as exact values, and verify our solutions. Also state restrictions on the variable. So to solve these, we're going to be looking at a couple different types. These first few are where every term involves a log. Every term involves a log with the same base in each question. So we can use the laws of logarithms to simplify each side. And that's what we're going to do first. In a situation where you have logs in all the terms, logs with the same base, use the laws of logarithms to get both sides down to a single log with the same base. So for question A, we could do that by using the quotient law because you're subtracting those two logs with the same base. That'll be log of x on 15. And there's no base indicated here, which means that both sides are base 10, but that part doesn't really matter. So here's what we're going to do next, okay? These two sides are equal. We're told that at the start, that the left side and right side are equal. Because the log with base 10 parts are the same, that means the other parts must be the same as well. We can say that x on 15 equals 0.2. So we're not using a mathematical operation to do this because you cannot, let's say, divide both sides by log base 10. That's not what we're doing. We're saying again, because the two sides are equal, we're told that at the start, that the two sides are equal. Well, if part of the sides are equal, the other parts must be as well. They both are logged with the base 10. Those parts are equal. So the other parts must be equal as well. So essentially, we're dropping the log base 10 from both sides. But it relates back to the fact that the two sides are equal. And if the log base 10 parts are the same, the other parts are the same or equal as well. So that's what we're really doing here. And then to get x by itself, you'd multiply both sides by 15. And 15 times 0.2 would be 3. And there's our answer. Now, we can check that in our calculator. Because these are common logs base 10, okay, the left side would be the log of 3 minus the log of 15. Log of 3, close the bracket after the 3, minus log of 15. Is that irrational number? Well, we should get the same irrational number if we go to the log of 0.2. And we do. So our answer works. Also, if we state the restrictions here, the only place we see the variable is in that first term, the log of x. And remember, you can't take the log of a negative number or of 0, so x has to be greater than 0. That's the restriction in this case. Okay, so there's the first one done. Question B, all four terms are logs with a base of 3. We've got 2 on the left of the equal sign, 2 on the right. We will use the appropriate law of logs to combine them. So on the left, we'd use the quotient law because those logs are being subtracted. And on the right, we'll use the product law. So it'll be the log of 3 times 5 with the same base of 4. So again, We've got both sides expressed as a single log with the same base. The two sides are equal. If the log base 4 parts are the same, the other parts must be the same or equal as well, meaning x over x minus 2 would equal our 3 times 5, which is 15. And I'll put that 15 over 1 because next I'm going to cross multiply. Whenever you have two ratios equal to each other, their cross products are equal as well, which essentially I did on the first question by putting the 0.2 over 1. When you cross multiply, you're going to get x equals 3. So I did the same thing. But here, because I have x's on both sides, I need to do some work to get x by itself. So when I cross multiply, subtract the 15x from both sides, and then divide both sides by negative 14, I'll get x equaling positive 15 over 7 when you reduce. Divide top and bottom by 2. So we can check this using our calculator. If you don't have the newer operating system, then you have to use the change of base for each term. But in this case, I will just use my log function. So it'll be log base 4 of x, which we found to be 15 over 7, minus, again, I need log with a base of 4 of 15 over 7, take away 2. So I'm going to use another set of brackets to keep the 15 over 7 together, minus 2. So that's what the left side equals. So that should equal the right side. Which is log base 4 of 3 plus log base 4 of 5. Same decimal. So our answer checks. Now, what about the restrictions? We have two arguments involving x. In the first term on the left is just log base 4 of x, so x has to be greater than 0. The second term, the argument is x minus 2, which also must be greater than 0, or x has to be greater than 2. We need to choose the one that satisfies them both, which is x is greater than 2. And our answer of 15 over 7 is greater than 2. That's another reason why it works. It satisfies the equation. So what's different about question A here is that the right side is not a log. But I'm going to start the same by using the laws of logs on the left to put those two terms together. That'll be log base 5 of x plus 1 times x minus 3, using the product law, or log base 5 of x squared minus 2x minus 3. Now from here we've got two options. We could make the right side a log with a base of 5. To make it equal to 1, it would be log base 5 of 5. And then you could drop the log base 5 from both sides. Or the other option is not doing that and convert from logarithmic to exponential. Start with the base and cycle through. 5 to the 1 will equal x squared minus 2x minus 3. Or x squared minus 2x minus 8 equals 0. If you made the right side a log by going log base 5 of 5, and then you drop the log base 5s of both sides, you would get x squared minus 2x minus 3 on the left, equaling 5 on the right, which is exactly what we have right below that. So either way, you're going to get the same expression. So we have a quadratic that we're going to factor. The factors will be x. That should have been, yeah, that's a 2x. That's a minus 8. It's x minus 4, x plus 2. So this gives us answers of 4 and negative 2. You should look back up at the original equation and immediately know that negative 2 won't work, because that would be asking you to take the log of a negative number. But to confirm that, we'll state our restrictions by taking each argument involving x. Remember that the argument has to be greater than 0. And we're going to take the one that satisfies both of these, which would be x equals or greater than 3. That's the restriction. Again, that's another reason why negative 2 doesn't work, because of what our restrictions are. Question B, I would probably start by collecting the logs together. I would subtract the log of x plus 1 from both sides. Bring it over to the left. And then we can use the quotient law to combine those two. And like we did in the previous one, I'm going to convert from logarithmic to exponential. This is a common log, which means base 10. So when you start with the base and cycle through, that base is 10. So it'll be 10 to the power 1 equaling 8x minus 4 over x plus 1. Make the left side a fraction so you can cross multiply. So subtract the 8x from both sides, bring the 10 over, and you're going to get x equaling negative 3. Which, if we look up at our equation, negative 3 won't work. We state our restrictions here. 8x plus 4 has to be greater than 0. 8x would have to be greater than negative 4. X would have to be greater than negative a half. Our other argument of x plus 1 must be greater than 0, so x would have to be greater than negative 1. Negative a half is the one that satisfies both. But our answer of x equals negative 3 is not greater than negative a half. In this case, there is no solutions. And you could also see that this is another way you could check, is using the graphing calculator. So y1 would be the log of 8x plus 4. Y2 would be 1 plus the log of x plus 1. If I go zoom 6 to set my windows to their standard settings, it doesn't look like they ever cross. Second function trace, number 5 for intersect, enter, enter, enter. There is no point of intersection, no solution. Okay? So you can also use your graphing calculator to verify solutions. So for the next one, I would start by, again, combining the logs. I would add the log base 2 of x minus 4 to both sides. And then use the product law to combine those. So this will give us log base 2 of x squared minus 10x plus 24. You know, and you could express the right side with a log of base 2. It would just take a little bit of work to figure out what that should be. In order to have a log with a base of 2 to equal 3, it would have to be log base 2 of 8. Because 2 to the power 3 equals 8. So you could do that. But you don't have to, because you can convert from logarithmic to exponential. Start with the base and cycle through. So 2 cubed is 8. When you subtract the 8 from both sides, you're going to get plus 16. And the factors there would be x minus 2, x minus 8. So therefore x would equal, according to that equation, positive 2 or positive 8. Positive 2 won't work though. If you let x equal 2 in the original equation, you'll be asking to take the log of a negative number. So 2 is definitely extraneous. We can check to make sure that 8 does work. Log base 2, and when x equals 8, 8 take away 6 is 2, so that part's going to be 1. That's the left side. On the right side, it will be 3 take away. Log base 2 of, again, when x is 8, 8 take away 4 is 4. So you get the same thing on both sides. So 8 works. We've confirmed that. And if we want to state our restrictions, take each argument and set it greater than 0. So that gives us x is greater than 6. The other argument involving x is x minus 4, which gives us x is greater than 4. So x is greater than 6 is the one that satisfies both. That's our domain. And again, our answer of 8 does fit that restriction. Okay. Question D. I probably use the power law here to bring this exponent of 2 in front. That's it, thank you. Because that now allows me to divide both sides by 2. So on the right side, when you divide the 4 by the 2 in front, that gives you 2 on the right. And once again, we will convert from, I'm good, thank you. No, not today, thank you. I will convert from logarithmic to exponential. So 2 to the power 2 will equal x plus 3. 2 squared is 4. So that gives us x equals a negative 1. Yep. Sorry. Positive 1. So, if we use the graphing calculator to check this graphically, so it's log base 2 of x plus 3 squared, and that should equal positive 4. So there's our positive one, but this shows a second answer. If I go -2, well, I'll try again. -4 as my guess. No, it keeps going back to the 1. So this point over here isn't a point of intersection. And that's why we only get one answer here when we check it. So if I go into the trace mode and I'm on the log function, okay, it looks like it's going to cross there, but again, when I check it, and this will come from our restriction, okay? Now in this case here, you have a non-permissive value of -3 only, because x plus 3 is all squared, so it'll never be negative. But you can't take the log of 0. And so it looks like there's a point of intersection here, but you see if I go into trace mode, which I am, and I'm on the graph of the log, if I let x equal -3, I don't get a y value returned because it's a non-permissive value. And that's the only non-permissive value here. Because the x plus 3 is squared, you're never going to get a negative value for that part, but you can get 0 for that part, and you cannot take log of a negative number. So our restriction here is that x cannot equal -3. That's our restriction. All right? So there's only one answer, and we checked that one already on the graphing calculator by finding the point of intersection. Oh, that gives us 2.75. -2.75. But that's not right. I don't think. But let's check it. When you let x equal -2.75, yeah, that's not going to work. When you let x equal -2.75, -2.75 inside the bracket, plus 3. Try that again. That's going to be 0.25. Positive 0.25. You're going to square it, and you'll get 1/16. If you take log base 2 of that number, the previous answer, you get -4, not +4. Okay, so it doesn't work. The only one that works is +1. What do you mean, put it in as it is?
So I went into my calculator and -2.75.
Yep.
I did it all in that one.
Yep.
So I didn't do it in separate steps. I just put log 2 and in those brackets I put -2.75 plus 3 and then I put square on the other side, and then just put in the entire thing and I got it.
Yeah, that's not right though, because -2.75 plus 3 is 0.25 or a quarter. So if you work this out, you'll have log base 2 of 1/4 all squared. 1/4 squared is 1/16. So that's log base 2 of 1/16. And that equals -4, not +4. I'm not sure why the calculator does that. Because no matter what, you're going to have the log of 1/4 inside the bracket. Yeah, I'm not sure why it does that. Shouldn't, because it should follow the order of operations. I'm not sure why that does that. Okay, so looking at question E. Again, this one you have the number 1/2. That's not a log. So I would start by combining the logs together on one side. And then using the product law, and this example illustrates why it is much easier at this step to convert to an exponential function. Instead of trying to write the answer or the number on the right, the positive 1/2 with as log with the base of 49, that's difficult to do. Not impossible, but difficult. Right? So it is better to convert from logarithmic to exponential. And so when you do that, you're going to have 49 to the power 1/2 equaling x squared plus 2x minus 8. (49 to the power 1/2 is the same as the square root of 49, which is 7. So when you subtract the 7 from both sides, there's our quadratic that we will factor. It'll be x plus 5, x minus 3. So the answers we get are -5 and +3. -5 won't work though. That'll give us the log of a negative number. So that one is extraneous. To check to make sure that 3 does work, we check just using the equation. When x is 3, 3 plus 4 is 7. And when x is 3, 3 minus 2 is 1. Log base 49 is 7 is asking 49 to what power is 7, and the answer to that is 1/2. 49 to the power 1/2. The square root of 49 is 7. And log base 49 of 1 is asking 49 to what power is 1? The answer is 0. 49 to the 0 equals 1. So that shows you that that answer of x equals 3 does work. Okay, but we also need to state our restrictions. And we need to take the one that satisfies them both, which is that x must be greater than 2. And once again, our answer of 3 does work. Okay? So on Wednesday, we'll do some more work with solving logarithmic equations. On Friday, we'll first do some examples dealing with exponential growth, decay, different formulas that involve logarithms. And then you guys will write your quiz after we go through the lesson. So, I mean, it'll be There's nothing on the quiz that's going to be based on what we're talking about on Friday. Okay, so, and then on Tuesday, we'll go through the Chapter 7 and Chapter 8 quizzes. You'll have time to work on your review assignment. This Thursday is your next unit exam on Chapters 7 and 8. Pardon? I have it now, so I can give it to you today. Okay. So